Welcome to MOOC program. Today we will discuss two reactions. First is one Birch reduction and second one is lithium aluminum hydride reduction. So Birch reduction is sodium or lithium metal in liquid ammonia. Generally this condition is treated. So reported in 1944 by Arthur Birch. That's why this reaction is called Birch reduction. An organic reduction of aromatic compounds to 1,4-cyclohexadiene in liquid ammonia with sodium or lithium and an alcohol like ethanol and tert-butanol, which are generally proton source. Radioselectivity of the products depend upon the nature of the substance of the aromatic compounds. And reaction proceeds via CET mechanism, which is called single electron transfer. Like if there is a substituted aromatic ring and when it is treated with sodium lithium metal in liquid ammonia with a proton source like alcohol, then you get unconjugated cyclohexadiene, and in one case the double bond, the R1 is present with the double bond carbon. When R1 is electron donating group, then you get this kind of system, and when R1 is electron withdrawing group, then the cyclohexide system has a saturated carbon here which constitutes the R1. So what is the mechanism of this reaction? When metal is added in liquid ammonia, then metal becomes M plus and liberates one electron, and this electron is stabilized by liquid ammonia. So that is the importance of liquid ammonia. It stabilizes the electron, and that electron then adds to the benzene ring, and you can see that first a radical anion will form, and this radical anion they wants to stay para to each other so that the repulsion will be minimum, and then this anion getting protonated by the alcohol, and the alcohol will be OR minus, and after protonation this hydrogen comes here, and then just a radical is formed, and that radical again one electron adds to the radical and it becomes anion, and after the anion is getting protonated by the alcohol and you get the cyclohexadiene system. And what happens when electron donor substituents are there? So if you have a alkyl group, OR group, NR2 group which are electron donating, and after treatment with sodium or lithium in liquid ammonia, you get the radical anion, and then this is the orthoprotonation and this is the rate limiting step. So the anion stays ortho position of the electron donating group, and that is why orthoprotonation happens. And now again this lithium liquid ammonia will come, then the radical becomes anion, and after that this anion stays to the meta position, because earlier I told that here the radical was formed, so they will be maximum para to each other. So ultimately this anion will stay here, and then that is why this is called metaprotonation. So first will be orthoprotonation and the second will be metaprotonation, and you get now this cyclohexadiene system where the substituents contains the double bond. So protonation of cyclohexadiene ions is kinetically controlled and occurs at the central carbon. So this is kinetically controlled process. Now if you have electron withdrawing substituents, what will happen? Now electron withdrawing substituents like carboxylic acid, ester, COR, ketone, amide, cyano, and aryl group also. That time also radical anion will generated, and now protonation it becomes a radical. And as I told here, first the anion will stay on the carbon atom which is connected to the W because that is stabilized by the W group, electron withdrawing, and now this anion will generated at the electron withdrawing group, and now initially this will be para protonation. So first will be para protonation, and now this will be ipso protonation later, but what I want to say that this anion can be generated also, and particularly when proton source is not there, then this radical anion becomes dianion, that is also possible, and this dianion later can react with the alcohol or ammonia, can get this anion, and this anion then the ipso protonation. So this is called ipso protonation. So this carbon atom where WT attached, they are the ipso protonation, or if you can treat with alkyl halide, then you can get the alkylation. So, alkylation also possible, and particularly only when the electron withdrawing group present in the aromatic system. So, aromatic carboxylic acid and carboxylase are readily reduced with lithium liquid ammonia in the absence of alcohol derivatives, and in the absence of alcohol derivative, this is the method that is following actually. So, dianion, and then the ammonia comes become anion, and then ammonium chloride. So, what are the reaction conditions? Metals you have to use lithium, potassium, sodium, occasionally calcium or magnesium, co-solvents like diethyl ether, THF, gly. Also proton source where appropriate, generally tertiary butanol or ethanol are most common, also methanol, ammonium chloride, even water can also be used as a proton source. And substituent effects already we have seen. Now, if you have this metamethyl anisole, then after sodium liquid ammonia and methanol, it gives 44% yield, because here this is the major electron donating group. This is the stronger electron donating group than methyl. So, this only controls the reaction, and you get the cyclohexadiene system where the methoxy group contains the double bond. Now, if you have a carboxylic acid already we have discussed that this is electron withdrawing group, and now if you have this metamethyl benzoic acid, then sodium liquid ammonia methanol condition, and after that if you treat with ammonium chloride, you get 94% yield of this product, where the carboxylic acid is present at the saturated carbon atom. So, for electron withdrawing substituents, the double bond will not be with the electron withdrawing group. So, electron withdrawing group will be on a saturated carbon atom. Reductive alkylation is possible. Reductive alkylation of aromatic compounds like this one, this is benzoic acid derivatives with sodium liquid ammonia in, then you add iodomethane, and then you get this cyclohexadiene system with a quaternary stereogenic center, and here the carboxylic acid and methyl groups at the same carbon atom. Reductive alkylation is possible with aromatic ester, amides, ketones and nitriles. So, they are all electron withdrawing groups. Then only the anion will be stabilized by the electron withdrawing group, and the alkylation is possible. Like this system, there is a ester and methoxy. Here the control will come from the ester group, and if you treat this compound with potassium, liquid ammonia and tertiary butanol, one equivalent which is protic source, and after treatment with 2-iodopropane, you get this isopropyl group here. So, this is the CO2 tertiary butyl. So, at the same center you get the isopropyl. So, you generate quaternary center here, and now after treatment with trifluoroacetic acid, you get the alpha beta unsaturated enone. So, what is happening here? So, TFA if you give, then what happens? This become enol, and this becomes CO2H first, and the decarboxylation will happen, and then you get the enol, you can write as a enone, a carbonyl compound, sorry, and now the decarboxylation is possible if you heat it, and now you get this one CH3, and now the isomerization will happen, which gives the conjugated enone. So, you get this compound. So, alpha beta unsaturated enone can be generated by reacting this ester with potassium ammonia tertiary butanol, then treated with 2-iodopropane, and this isopropyl substituted enone you can generate. Also, if you have a cyano and methoxy a substituent in the compound with treatment of lithium, ammonia, THF and tertiary butanol 1 equivalent. And after that, if you treat with 3-chloro-1-bromopropane, then you get this compound. So, here this is the electron withdrawing group. So, the substitution will happen on the electron withdrawing group, and here since bromine is a good leaving group compared to chlorine. So, you get the bromine elimination, the substitution happens under this carbon atom and you get this product with a chloro substituent. Aryl silane also on reaction with lithium liquid ammonia in ethanol, it gives this cyclohexadiene system and this acts as a electron withdrawing. So, the anion is stabilized by SiAmi3 group. So, this means that SiAmi3 acts as electron withdrawing group, and now if you treat phenyl trimethyl with lithium liquid ammonia ethanol, then you get 76% yield of this cyclohexadiene. Now, if you have a methyl substituent, then also you get this compound. Here SiAmi3 will be there. SiAmi3 will be on the saturated carbon atom, and when 2,6-dimethyl substituent is there, then you get 70% yield of this product. Also, when you have paramethyl group, then you get 70% yield, and interestingly, when two SiAmi3 group are there, then one SiAmi3 eliminates and you get cyclohexadiene system with SiAmi3 group with a double bond. Pyrols can also react with these conditions. Now, we will discuss first two substituted pyrols, and R2 is generally ester. So, this is generally ester or amide group which is electron withdrawing. So, this is EWG. And now, if you treat this two substituted pyrrole with sodium liquid ammonia THF with tertiary butanol followed by alkylation with methyl iodide, then you get 2,5-dihydropyrrolidine, 2,5-dihydropyrrole with a quaternary center at the 2 position, and the major product is this with ortho position aldehyde group also. And you can see here, if R1 is equal to methyl and R2 is equal to pyrrolidine. So, if it is a pyrrolidine amide, then you get 25 to 30% yield of the product. And if R1 is equal to methyl and R2 is equal to O isopropyl. So, this is amide and this is an ester. So, you get 20% yield of the product. So, yield is very not good. Now, if you have a 3 substituted, suppose here the electron withdrawing group at the 3 substituted, and interestingly, now the desired reaction happens. However, you get 2,3-dihydropyrrole, and here the electron withdrawing carbon, there the alkylation happens. So, here electron withdrawing group was earlier in the 2 position, there the alkylation happened. Now, it is at the 3 position, and 3 position the alkylation happens. And now, if R1 is equal to Boc and R2 is equal to pyrrolidine. So, if it is a pyrrolidine amide and R3 is equal to methyl, if the alkylation with iodomethane, then you get 70% yield. So, this is with iodomethane. And now, again you have a Boc group and pyrrolidine amide. Now, if you alkylation you do with benzyl bromide, suppose. Now, we get 69% yield of the product. Now, what will happen with 3,4 disubstituted? Like 2 ester groups are there at 3 and 4 position, 3 and 4. Interestingly, when this compound is treated with lithium liquid ammonia THF and then alkylation with RX, interestingly the disubstituted means the disubstitution happens and 2 quaternary. So, this is vicinal quaternary centers. So, 2 quaternary centers side by side, and also their stereochemistry is cis. So, cis is the major, as you can see. When R is equal to methyl, suppose iodomethane, you get to 77% yield, and cis is to trans is to greater than 20:1. So, cis is the major product. Now, if you have ethyl iodide, then you get greater than 10:1 cis product and 82% yield. If it is allyl bromide, then you get greater than 10:1 for the cis and 70% yield, and if it is isobutyl, then also you get greater than 10:1 and 79% yield. So, the cis substitution is important. So, always you get the cis as the measure. Now, if you have a two different alkyl halide, like first one is with R1 and second one is with R2, that also you can do. Now, you can one carbon will contain R1 and another contain R2. Suppose if you treat first the in the system with after lithium ammonia treatment, if you add first the isobutyl iodide and then iodomethane, then you get the product 82% yield. So, this is symmetrical compound, does not matter where R1 comes first, you get the same compound, but the geometry is important, cis. Now, again if you treat with isobutyl iodide and then benzyl bromide, here also you get the product cis product with 77% yield. Not only pyrols, indoles can also be treated with this condition, and here this N-methyl indole, if you treat with lithium ammonia, ammonium chloride as the proton source. So, this is the proton source. Then the reduction happens in the heterocyclic ring. So, heterocyclic ring is reduced, and this is very important. The Birch reduction here, electron is the reducing agent, not hydrogen source. So, the electron adds to this system and reduced. So, this is the reduction of heterocyclic ring, and here when you treat with lithium liquid ammonia with methanol excess, methanol is a proton source now, here reduction of carbocyclic ring is observed, and here an isolated double bond is there. So, this pyrrole is there, N-methyl pyrrole motif, and here a cyclohexene motif is present. Quinolines also can be treated with this condition. Suppose here two equivalent lithium liquid ammonia, ammonium chloride or R2X, here the N alkylation is possible and the heterocyclic motif is reduced and only one double bond is present. So, this is like enamine system here, and now you can see if R1 is equal to H, that means this is with quinoline only. So, if you do the reaction with quinoline and then different alkyl halide, suppose iodomethane 88% yield, and the alkylation happens on the N atom. So, the N alkylation is happening, like isopropyl 78%, benzyl group 45%, CH2OMe 79%, CO2Me 78% yield. So, here N alkylation is happening, N alkylation. Now, if you increase the amount of lithium, so what will happen? 5 equivalent lithium, ammonia and methanol as the protein source. Now, you get a mixture of products. In one case, the heteroaromatic group or heterocyclic group completely reduced, and another case this group partially reduced, the cyclohexene, the benzene group. So, here if R1 is equal to 7 methoxy or hydrogen, you can get this kind of products. Furan also can also be reduced under Birch reduction condition. Here two substituted, furan first used, and CO2H, we know this is electron withdrawing group. And now, after treat with 2.5 equivalent lithium, liquid ammonia condition at -78, then you treat with alkyl halide or ammonium chloride, which is a proton source, and you get 2,5 dihydrofuran. 2,5 dihydrofuran, and at this 2 position, here the quaternary center is formed. If you treat with alkyl halide, suppose if you have a methyl, suppose if you treat with iodomethane, you get 75% yield of this product. If it is isopropyl, that means 2 iodopropane. If you do the reaction, then you get 95% yield. So, yield gets enhanced. Now, if you treat with benzyl bromide, then what will get 75% yield, and if a proton source like ammonium chloride is treated, then you get answer means only carboxylic acid will be there. This will be not a quaternary center, but this will be a stereogenic center, you get 80% yield. 3 substituted, suppose if the carboxylic acid at the 3 position, then like our earlier case, pyrrole case, here also, here the reduction will change now. So, now you will get 2,3 dihydrofuran, because your 2 or 3 position formally hydrogen had been added. So, sodium, liquid ammonia and 8 equivalent of isopropanol, ammonium chloride. So, this is the proton source. So, here this proton comes from ammonium chloride, and now that ester you can convert to the carboxylic acid you can convert to ester with treatment with diazomethane, you get the methyl ester. And this compound can be converted to a biologically active compound, which is autoregulator of plus A factor like this. So, this you can derivatize to this compound. Alternatively, if you treat this compound lithium, ammonia, ammonium chloride, no added proton source, so no isopropanol, then what will happen? Then the butyrolactone is derivative is formed. So, butyrolactone. So, butyrolactone derivative is forming. So, here this compound completely reduce, the furan motif is completely reduced to give a saturated compound, which is called here butyrolactone. And now, if you have a 2,5 disubstituted furan, so this is 2 and this is 5, and now again you get like earlier 2 substituted, here also you get 2,5 dihydrofuran, and depending on R you get different yield. Suppose R is equal to methyl, you get 83% yield, and in this case the selectivity is not good, 1:1 cis trans mixture, because this is a stereogenic center, this is a center. So, cis and trans will be 1:1 mixture. If alkyl halide is ethyl, then you get 85%, here also 1:1. If it is N-propyl, then also 1:1, tertiary butyl 1:1, benzyl group 3:2, and the yield also got reduced 40%, and this is a paramethoxy benzyl group, the yield is 40% only, and 3:2 is the ratio. So, cis is the measure, but cis is marginally measured in some cases. Asymmetric Birch reduction also is possible, like you have this kind of chiral compound, there is a amide group, this is amide group, this is ether, and now if you treat with lithium or sodium liquid ammonia THA followed by tertiary butanol 1 equivalent, then you get this kind of enolate, conjugated enolate system. Now, this is the proposed convex attack. So, the convex side is open and the alkylation happens from the top face. So, top face is open and the attack will take place from the top face. And you can see the selectivity, if it is methyl iodide you get 67% yield, this is 60% yield of the product. Now, if it is ethyl iodide then you get 82% yield and greater than selectivity, this is diastro enhancer selectivity. So, 98% selectivity you get. PaCH2, if it is allyl bromide you get 75% yield, greater than 96% selectivity, benzyl bromide you get greater than 96%, and this is another alkyl bromide you get 96% selectivity, and if it is a ClCH2CH2Br you get 91%, and this is not measured. Now, if you clip this ether and their ether motif is, this is open now. Now, what will happen? Now, the product will be different. Here also lithium liquid ammonia you get the dienolate. Now, the control will come from this CH2ME group. Since it is in the top phase, the reaction will take place from the downside. So, down phase attack. and R group will come from the downside, and you get this kind of cyclohexadiene system, and here Rx can be defined like earlier case methyl iodide, ethyl iodide, benzyl bromide. This is another alkyl bromide, this is Cl and Br containing alkane. And here that is the important thing, opposite facial selectivity is observed. So, when it is a cyclic system, then you get the convex attack, and now you get the concave attack when it is open. Also, if you replace, earlier it was A star, now if you have a amide here, now if you treat this compound with potassium 4.4 equivalent, liquid ammonia THF tertiary butanol 2 equivalent, you get this kind of enolate, conjugated enolate, and now ammonium chloride treatment, the hydrogen comes from the top side. However, when alkyl halide is there, then the alkylation takes place from the concave attack. So, from the concave side, so it is attacking from the downside. And here the selectivity you can see, if R1 is equal to hydrogen, R2 is equal to hydrogen, alkyl halide, if methyl iodide, it get 50% yield and 70% selectivity. So, selectivity is not very good like earlier, but still you get 70% selectivity. With ethyl iodide you get 82% selectivity, and with ammonium chloride, when R1 is equal to methyl hydrogen ammonium chloride, you get 84% yield and only one diasteromer. So, this is very important. When R1 is equal to methyl, so this is methyl group, this is methyl and this is hydrogen, then you get only one diasteromer for this product. And similarly, for this product you get methyl iodide treatment, but you get the selectivity only 52%. However, when you change the alkyl halide to allyl bromide, then 95 is to greater than 95:5 selectivity you observed, both methyl iodide, allyl bromide as well as benzyl bromide cases. This is another chiral auxiliary was used for N-Bock pyrrolidine derivative, N-Bock pyrrole derivative, like here 8-phenyl menthol is used as a chiral auxiliary, and this is actually EWG, 2 position EWG is there, and we know the 2,5-dihydro pyrrole will form. And here if you treat with alkyl halide, this will be a quaternary center, and alkylation will happen to this carbon, orthocarbon of the 2 position. And this 8-phenyl menthol you can cleave with TFA. After that you can treat with sodium hydroxide, and then again you have to treat with Bock, because Bock will eliminate when TFA is treated, and now the Bock protection again you have to do, and you get this carboxylic acid. And you can see the selectivity, if R is equal to methyl, with iodomethane you get 79% yield, 78%, and if R is equal to ethyl iodide, then 86% E you can get. Isobutyl case you get 90% enhanced selectivity, and CH2PHG benzyl group is added, then you get 90% enhanced selectivity. So, depending on the group, so E increases, that is the steric. Now, if you have a chiral auxiliary, this is C2 symmetric chiral auxiliary, and now if you treat this compound with sodium liquid ammonia and -78 degree centigrade, you get this enolate, and now this enolate will react with Rx, and this group which is closer here, if you see this group, this is top side, now this will be down. So, the alkylation will take place from the down side, and this is also 2,5-disubstituted furan, 2,5-dihydrofuran. And now if you treat with 6-normal HCl, then this chiral auxiliary cleaved, and you get a carboxylic acid, and depending on R, if it R is equal to methyl, then you get greater than 94% enhanced selectivity with 86% yield. If R is equal to ethyl, then you get greater than 94% enhanced selectivity, 74% yield. If it is isobutyl, here also you get greater than 94% enhanced selectivity with 68% yield. Now, we will discuss lithium aluminum hydride reduction. So, this is the structure of lithium aluminum hydride, lithium plus Al4 hydride actually are there. It was discovered by Feinhold, Bond and Schlesinger in 1947. It is a colorless solid, but commercial samples are usually gray due to contamination. So, whatever we see in the lab, that is gray color because of contamination. Non-selective reagent for hydride transfer reduction, all carbonyl groups are reduced generally, many other functional groups are reduced or eliminated. Reaction with acidic protons generates hydrogen. So, Potic solvent cannot be used. Then lithium aluminum hydride will be quenched. Generally, the reactions are performed in ether solvent due to better solubility and also low temperature because it is quite vigorous. So, how lithium aluminum hydride is prepared? It was first prepared by treating lithium hydride 4 equivalent with aluminum chloride, you get LiAlH4 and 3 molecule of lithium chloride as a byproduct. In industrial scale, it is prepared from sodium aluminum hydride. So, sodium aluminum hydride, which is prepared by reaction of sodium, aluminum and hydrogen at high temperature and pressure. So, at high temperature and pressure, you get hydrogen with aluminum, the bondage happens. And now, this sodium aluminum hydride treated with lithium chloride, you get the exchange. So, lithium aluminum hydride is formed and sodium chloride is the byproduct. Overview of LH reduction. LH can reduce various carbonyl groups. Here aldehyde is used, here ketone, here ester. So, aldehyde goes to first the alkoxide, then proton source comes, you get the alcohol. Similarly, with ketone, you get the alkoxide, and now proton source comes, you get the alcohol. Ester case, this group will eliminate, you get a alkoxide here after elimination and reduction, and then again proton source, you get the alcohol. So, aldehyde, ketone, ester, all cases you get alcohol. If you have a azide, then you get the amine. If you have a carboxylic acid also, this OH group will eliminate, you get a alkoxide, and which is treated with protein source, protic source, you get the alcohol. Also, nitrile can be reduced to amide, even amide goes to amine. Epoxide can be cleaved to alcohol, generally less hindered phase it attacks, you get a alcohol at the secondary carbon. So, reduction of aldehyde and ketone, generally aldehydes and ketones are reduced with lithium aluminum hydride to get their corresponding alcohols. And if you have a ketone like this with a bromo substituent, now lithium aluminum hydride ether minus 78 degrees centigrade, this substituent is untouched, only the keto group reduced to the alcohol. What is the mechanism of carbonyl reduction? Now, here it is important that the both aluminum and lithium binds with oxygen, and lithium actually in fact activates carbonyl. It has been observed that addition of a crown compound can prevent reduction by removing lithium. So, if you remove lithium, then the reduction will not happen, and then this hydride, their hydride bond is there between aluminum and lithium, and this hydride is coordinated at this carbonyl carbon, and now the hydride delivery will take place to generate the alkoxide derivative, where bond like this will be there, first aluminum hydride lithium, and this will goes to H3Al negative charge here. Now, you can see this is also a reducing agent, there are 3 hydride is present. So, it can react another 3 molecules of carbonyl compound, ultimately 4 molecules of carbonyl compound gets reduced, and you get a alkoxide like this, where Al minus will be coordinated to 4 oxygen atom. Number of repetition depends on sterics of the carbonyl group, this is important. Also, each addition is slower because alkoxide electron withdrawing group, so reduces reactivity of hydride. So, so this reaction, this is reactivity less. So, reactivity less compared to lithium aluminum hydride. And ultimately, if you treat with proton source, then you get the alkoxide to alcohol. Reduction of acids, various acids can be reduced with lithium aluminum hydride. Here you can see cyclobutane carboxylic acid reduced to the alcohol with lithium aluminum hydride THF, and then treated with protic source. And here an amino group is present and a carboxylic acid, this is alpha amino acid, it is reacting with lithium aluminum hydride THF in reflux condition, followed by acid treatment gives the alcohol. And here a cyclohexyl group carboxylic acid is present, here lithium aluminum hydride reduces under reflux condition to the alcohol, and this is a quaternary center. Here a phenyl acetic acid like group is there, and this on reduction with lithium aluminum hydride generates this primary alcohol. Esters and amides can also be reduced. Generally esters on reduction clip this and generates 2 alcohol. This is one alcohol, this is another alcohol. Amides, this carbonyl gets to CH2, so you get a amine. Here 2 alcohols are generated. What is the mechanism of this reaction? So, amide, first this carbonyl group gets reduced to generate the alkoxide, and now this alkoxide on elimination of will generate imine, and imine will be activated again like carbonyl compound. This aluminum will bind to the imine and hydride delivery at this carbon, imine carbon, and you get ultimately amine. Alternatively, this hemiketal or aminal will be formed after protonation, and this can clip, the hydrolysis can happen, and you get hydrolysis, on hydrolysis you get secondary amine and carbonyl compound. So, this is also possible. So, secondary amine and carbonyl compound. So, instead of a amine, you can get this also side reaction. This is an example that lithium aluminum hydride is used in many complex structure. This is a complex structure where there is a enone motif, also there is a amide motif, and you can see with lithium aluminum hydride THF reaction you get the amide to amine. So, amide to amine happens here, and selectively the carbonyl group is getting reduced to alcohol, and also the geometry of the compound, this reduction happens diastero selectively. So, diastero selective reduction happens, the hydride comes from the down phase, and here you can see a silyl group is present and 2 ester motifs are present, both ester getting reduced with lithium aluminum hydride, you get a diol without disturbing the tips group. Here is another example, here a carbamate group is there. So, this is carbamate, and here a carboxylic acid. So, in protected amino acid is present. Now, the carboxylic acid goes to the alcohol, and carbamate also getting cleaved. Carbamate cleave is giving you a primary amine. So, carbamate cleaved or cleaves. Carbamate cleaves under this condition, and this is an compound where is a lactone is there. Lactone on lithium aluminum hydride reaction, it gives diol. So, this is very important, this bond is getting cleaved and you get a alcohol aldehyde, then that instead to generate aldehyde get reduced to the alcohol. Also, if you have a many ester groups like as well as carboxylic acid, here is an ester, here is an ester group, and all groups with lithium aluminum hydride reflux condition getting reduced, this alcohol, this alcohol, this alcohol, and this alcohol. Reduction of azides, nitriles and nitro compounds. So, azides, nitriles and nitro alkanes on lithium aluminum hydride reduction generates the amine. What is the mechanism of the reduction of nitriles to amine? Here also the nitrogen binds both with lithium and aluminum, and now this hydride delivery will take place to generate first the imine with an aluminum bond, and now this can again reduce another nitrile to generate this species where 2 imine bonds are connected to aluminum, and ultimately this imine will get again reduced. So, on reduction you generate the amine, and after protonation you get the free amine. So, this is the free amine. So, what is the intermediates? Nitrile goes to imine goes to amine, and after proton or acidic workup you get the free amine. Example like here, this is an enamine, enamine with K plus and cyanide nucleophile. First in the protons, when you get the acidic medium pH is equal to 3, then you get the iminium ion. And now the cyanide adds to the iminium ion to get this cyano containing product, and now LDA can take this proton and generate an anion, and after alkylation you get this compound. Now if you treat this compound with lithium aluminum hydride, what will happen? This bond will cleaved. So the aminal is cleaved to this free alcohol. Also, if you make the nitroalkene, now with treatment of lithium aluminum both nitro and a double bond, the first reduction will take place of the double bond, because this is the double bond is activated. So activated double bonds can be reduced with lithium aluminum hydride, and ultimately you get the amine. Here a nitrile is there with lithium aluminum hydride reaction followed by acidic quark, you get the amine. Here is a more example, like a secondary azide is there with lithium aluminum hydride condition, you get a secondary amine. Here also azide is present, you get a primary amine, and after acetic acid you get the cleavage of the ketal, you get free diol. Epoxide ring opening is a very important reaction, and here the regioselectively at the least hindered end. So here the hydride will take place from this side. Epoxides are more readily reduced than esters. If you have ester functionality and epoxide, then epoxide will reduce fast. On the other hand, if aldehyde, ketone and epoxide is there, then the reduction will take place on the aldehyde and ketone, because epoxides are less readily reduced. Example, here is an epoxide is there, lithium aluminum hydride treatment gives this alcohol with a quaternary center here. Here also regioselectively the cyclohexene epoxide then gives this quaternary center, and this complex molecule when treated with lithium aluminum hydride, then hydride delivery takes place from the side. You get this secondary alcohol. Also the ester group getting reduced to the alcohol. Epoxide ring opening, more examples is there. If cyclohexane system is there, and if you have a epoxide like this way, if you draw in the downside, then the hydride delivery takes place from this side. So hydride comes from here. So axially, mostly it attacks at axially. Strong preference for axial attack, transdiaxial ring opening. Suppose this system, if the epoxide is up now and this becomes equatorial, this axial, so hydride will come from this one axial side, you get this alcohol. Here it is down, here it is up. Hydrogenolysis transformation also lithium aluminum hydride does, like X is equal to bromine, iodine, bromine, chlorine, O tosyl, O methyl, O triplet, you get this alkane. Examples like benzyl bromide on treated with lithium aluminum hydride THF and followed by acidic workup, you get toluene. Similarly, cyclohexyl bromide with lithium aluminum hydride THF 65 degrees centigrade followed by acidic workup, you get cyclohexane in 96% yield. And this is a normal long chain alkyl bromide also with lithium aluminum hydride H3, you get the alkane. Reduction, if you have a cage compound like this, then this chlorine can be removed with lithium aluminum hydride reflux condition. And also if you have a diol, now if you selective protection of this primary alcohol to the tosyl derivative, and then lithium aluminum hydride reduction can remove this O tosyl group, so that the alkyl group is generated here. Generally, LH does not reduce alkenes or alkynes, but we have seen the activated alkenes get reduced. Suppose if you have a compound like this 2-chlorocyclohexanone, and if you treat with this propargylic Gigner reagent and with THF minus 70 degrees centigrade followed by lithium aluminum hydride and H2O condition, you get this alcohol, where a triple bond becomes double bond. Similarly, here also triple bond addition and followed by reduction generate this diene, and here also the triple bond becomes double bond. So what is the mechanism of these reactions, that we will see. So first carbonyl group is getting attacked by this Gigner reagent to generate this alkynyl chloroalkoxide, which after treatment with lithium aluminum hydride generates this reduction happens like this. So, the aluminum selectively hydride, it selectively come from this way, so that aluminum will be there or this carbon atom, and it can bind with the oxygen. So, this is called vinyl alanate, and after pinnacle like 1,2 rearrangement you get a carbonyl compound. So, it will be like this. So, carbonyl compound and you get this one. So, this is a SN2 substitution reaction, here you get from the alpha attack, and after that, after acidic workup you get a double bond here, which is trans. So, the reaction passes through an alkynyl chloroalkoxide, which when treated with reducing agent is hydroaluminated to yield vinyl alanate, which subsequently undergoes a facile pinnacle like 1,2 rearrangement. Excess hydride reagent reduce the intermediate alkynyl ketone, and the resulting 2 alkynyl carbonyl is isolated on aqueous workup. This is the similar process here also happens when you take propargylic alcohol with lithium aluminum hydride, you get a trans allylic alcohol. So, here proximal alcohol is necessary, and the reaction passes through a trans selective hydrometallization of the triple bond, releasing the alkene on proteolytic workup. So, this is the mechanism that alcohol binds with aluminum, and the hydride delivery takes place from this side. You can see this is the hydride, and now this species will be generated after elimination of hydrogen, and now after proton source you can see this is the trans, actually this and this they are trans to each other. So, you get a trans allylic alcohol. So, whatever we have seen today, the first is the Birch reduction. So, in the Birch reduction we have seen that benzene derivatives can be reduced, and when depending on the substitution you get two kind of cyclohexadiene system. If you have a electron donating group, then the double bond will contain the group electron donating. On the other hand, if electron withdrawing group is there, then the cyclohexadiene system will be generated, where electron withdrawing group will be on the saturated carbon atom. Also, we have seen that chiral Birch reduction is possible, like you have a substituent, then you can do an Birch reduction followed by alkylation, and it is only possible when electron withdrawing group is present, and you can generate the quaternary center. And this reduction was successfully applied to furan, pyrrole, indole, quinoline system. On the other hand, lithium aluminum hydride is very strong reducing agent, and it reduces all kinds of carbonyl compounds, aldehyde, ketones, esters, amides, nitriles, azide and nitroalkanes gives the amine. On the other hand, if you have a allylic alcohol with propargylic system, then you can get a trans selective allylic alcohol, and this is the mechanism follows that aluminum bind with the alcohol, and then a 5-member ring is formed. So, also generally this is important that the double bond can also be reduced with lithium aluminum hydride, particularly when it is conjugated, like nitroolefin on reduction with lithium aluminum hydride, both nitro and the double bond gets reduced. So, this is the difference between Birch reduction and LH. In Birch reduction, the electron is the reducing agent. On the other hand, lithium aluminum hydride, the hydride minus is the reducing agent. Thank you.